This is the second lesson in a series of lessons introducing the use of bipolar transistors for amplifiers. And so we're going to begin in this second lesson to solve some large signal examples. So exercise or example 1.1. Let's say that we have a PNP transistor that's grounded and has a current source that is 1 microamps. This is pulled up to 7 volts, and we have a 10 kilo ohm resistor. We're going to assume this transistor, call it Q1, has a beta of 100. We are told that it has a VBE equal to 0.7 volts at 1 milliamp collector current. Okay, so that's the collector current. Now we are to find this collector voltage. Now if we know that the beta is equal to 100, then we can say that if in saturation, if in active region, which we'll assume, then IC is going to be beta times IB, which is going to be 100 times 1 microamp, or 100 microamps, 0.1 milliamps. Then we would say that VC is equal to 7 volts minus 10K times IC, which is 0.1 milliamps. So therefore we would have 6 volts. Then we ask ourselves, is the transistor actually in the active region, or is it saturated? Well, since VC equal to 6 volts is greater than VCE sat, which I didn't specify here, I guess I should say VCE sat is 0.2 volts, but we'll assume that if we're not given it, because VCE equals 6 volts and is greater than VCE sat, therefore in active region or mode, and where our problem is done, VC is equal to 6 volts, and if we wanted to find VBE, we would have to do a little bit of work here. So let's see, how might we solve that? Well, we could write that IB is equal to IS over beta times e to the VBE over VT. Now we know that VBE is equal to 0.7 volts at IC is equal to 1 milliamp, which is the same as saying IB is equal to 1/100th of that, so 10 microamps. So therefore we can use this Shockley diode relationship that would say V2 minus V1 is equal to 1 general N times VT, but this is 1 for the transistor, times the log of I2 over I1. So here we have V2 would be V1 is plus VT log of I2 over I1. So all we're doing is we have a diode curve, I and V. We have one data point here, and we're trying to find another point on the curve using that first one. So V2 is going to be equal to V1, which is our 0.7 volts, plus, and we'll assume 25 millivolts, times the log of I2. Now is the, what is I2? I2 is 1 microamp, right? Because our base current in this problem is 1 micro, not 10 microamps. This evaluates to 642.4 millivolts. So the log is negative, and as we would expect, we were up here at 10 microamps, and now we're down at 1, and we had 0.7 at 10 micro, and at the 0.1 we have 0.64 volts. So we'd say VBE is equal to 0.64 volts, and it's rounded out. IC is equal to 100 microamps. Let's look at a second example. In this problem we have an PNP transistor, and instead of having a current source connected to the base, we have a voltage source. So if we look at this a little more closely, we see that the voltage between the emitter and the base is 10 minus 9.25, so we have 0.75 volts. So in this case, we have to use the exponential large signal model for the transistor, because we certainly can't assume a base emitter or emitter base junction voltage of 0.75 as we are forced, or 0.75 is forced upon us. So we're going to use the Shockley equation again. Previously we had the V2 minus V1 equal to NVT times log of I2 over I1. Now we're going to re-express this as I2 over I1 equal to e to the V2 minus V1 over NVT. So we will have I2 is going to be equal to I1, which here we're told again we have a 1 milliamp transistor, and so it'll be 1 milliamp times e to the, so V2, the new voltage that we have, is 0.75 volts, minus V1, the voltage that we are given, 0.7 volts, divided by 25 millivolts. So that's 50 millivolts divided by 25, so that's 1 milliamp e to the e squared. So that will be 7.39. So therefore IC is equal to 7.39 milliamps. And therefore we can write that VC is equal to 0.5 kiloohms times 7.39, which is equal to 3.69 volts. If we wanted to, let's see what else is there to know. I guess that's it. If we wanted to know the base current is going to be the collector current over beta. So that's over 100. So we'll have 73.9 microamps. Let's now look at a third example. Here we're back to an NPN transistor, but we have, oops, I didn't finish this here. We have the base grounded through a 10K resistor. So this is the new element here, having a resistor in the base. And just to mix it up a little bit, we actually have the collector, the emitter, at minus 5 volts rather than being at ground. And again, it's the same transistor, beta of 100, VBE of 0.7 at IC of 1 milliamp. We've already found that at 0.1 milliamps, the VBE is 0.64, and right up here, I went ahead and computed what the VBE would be at 10 milliamps, and it turned out to be 0.7, about 0.76, so that we see the span basically from 0.64 to 0.76 volts as we span 2 decades of current. We can look at this a little more generally. This will just help guide us as we go forward here to help us know when we have to use the full exponential large signal model and when we can assume a constant VBE. And if we take our Shockley relationship here and replace the natural log with 2.3 times base 10 log, and now if we assume that the two currents that we're comparing here, operating currents, are order of magnitude apart, then we find that the difference in voltage between the two is 2.3 over 40, because 25 millivolts is about 1/40th of a volt, and this comes out to be roughly 60 millivolts. So as a rule of thumb, VBE changes about 60 millivolts per decade of IC, of current. Okay, so now let's look at this particular problem. We need to find VC again, so what we really need is IC. So we need this current here, and we realize that if we're going to solve this properly, what we have really, I'm going to redraw this base circuit. I'm going to put the 5 volts over here. If you don't see, this isn't obvious to you, stop the video and think about it for a moment. But the original circuit has 5 volts, a net 5 volts in the loop that comprises the base emitter, or base resistor, the base emitter junction, and the voltage source. So I've just redrawn it here. So what we have essentially is a load line where we plot voltage vertically versus current on the horizontal. We have an open circuit voltage of 5 volts. We'd have a short circuit current of 5 volts over 10K, so that would be half a milliamp. And then we have our VBE diode, that curve that is exponential. And to solve this, we have to use some kind of a numerical method because this is a nonlinear circuit. So you can either use a computer calculator, or you can use some kind of iterative method and do it by hand. And we want to, in general, avoid this unless it's absolutely necessary. So in this case, I'm going to show that it is not necessary. So let's just make an assumption on the VBE voltage for a moment. If we assume that it was 0.7 volts, then we could easily calculate the base current. It would just be 5 minus 0.7 over 10K, so that would be 430 microamps. Now if we were off on that 0.7, then, and let's think about now, if it changes by 60 millivolts per decade, okay, so we'd think, what if we were off by an entire decade? Then we would have, instead of 0.7 volts, let's say that we had 0.64 volts, okay, then our current would be 5 minus 0.64 over 10K, and that would give us what, 436 microamps. No, I didn't do that right. I did do that right. Okay, it only changes by 6 microamps, right, which is essentially 1.5%. Okay, and that's if we were off by an entire decade, which clearly we can't be, because even changing the voltage by a full decade of current only changes our current by 1%. So we are going to assume our voltage of about 0.7. Now, in this particular example, let's see, we have, if the base current is 430 microamps roughly, then the collector current would be beta times that, right? So it's going to be 43, IC is going to be 43 milliamps. And I chose values poorly here because in this case that will mean that VC is equal to 10 volts minus 43 times 1K, so it's minus 43 volts, and clearly the transistor is not going to be in the active region. So let me cheat now and change this collector resistor to 100K, right? That'll clean things up. So now we will have VC is 10 volts minus 0.1 K times 43 milliamps. So that'll be 10 minus 4.3, or 5.7 volts. So our collector voltage will be 5.7. Now we saw, or we were given that at 0.1 milliamps, at 1 milliamp, the transistor had a VBE of 0.7, and since we are roughly a decade above that current, we're roughly at 0.76 milliamps, or 0.76 volts. But again, that is not going to make a significant change in our current. It'll be a 1% or so error. And so this is a good example where we can make use of the constant VBE model, and it greatly accelerates the biasing solution for the circuit in question. In this fourth example, we're back to using a PNP transistor. And again, we have a base resistor. So this is going to be very similar to problem 1, or example 1.3. And off the bat, what we want to look at is when you look between the emitter and the base, and you look at the loop that is for which that VBE junction is part of, you want to look for the total voltage that's driving that loop. So in this case, what we really have, if you go around this loop, we see that we really have a 30 volt source here. 30 volt source that is driving all of this. So that right away, that clues us in on, 60 millivolts per decade. That type of voltage is going to be very insignificant compared to the 30 volts, and so we are going to, right off the bat, assume a constant VBE model. So assume V, in this case, is going to be VEB because it's a PNP transistor. So VEB is 0.7, and so immediately we can write the base current is going to be approximately 30 volts minus 0.7 volts over 0.1 mega ohms, and so that's going to be 29.3 or 293 microamps. With beta of being 100, we'll have the collector current being approximately 29.3 milliamps, and therefore the collector voltage will be just 0.5 kilo ohms times the 29.3 milliamps, which is going to be 1465 volts, if I did that correctly. We always want to check at the end that the transistor is actually in the active region, so we can write that VCE, oh no, in this case we'd say VEC, because it's a PNP transistor, is going to be equal to 30 volts minus 14.65, which is, approximately 15 volts. So this is much greater than VEC sat. So clearly we are in the active region. We now want to look at a somewhat different structure of a circuit. We're back to an NPN transistor, and we have a 5 volt source again driving the base, but instead of having a base resistor, that voltage source drives the base directly. However, the emitter now is no longer grounded. So if you go back and look through the other examples, all of the other examples, the emitter, whether it was an NPN or PNP transistor, was actually grounded. It was either tied to ground or it was tied to a supply rail. This is the first instance where we have a resistor between the emitter and the and ground, or a voltage source. Now you might think initially, well, we're going to have to use the large signal exponential model because we have a voltage source connected to the base, but recall that we only need to use the exponential large signal model when there is a hard voltage source that is being driven across the base to emitter junction. And here that is not the case, because although the base is tied to the supply, the emitter is connected to that supply, or to ground, through a 1K resistor. And so we will be able to use the constant VBE model again. We start out by looking at the loop in which the base emitter junction is involved, and we see that there's 5 volts total driving it. So again, we're thinking the 60 millivolts per decade is approximately 1% of a 5-volt source, so we're going to assume the constant VBE model. So what do we have here? We have approximately 0.7 volts between the base and the emitter, and so if that's the case, then we have 4.3 volts across our emitter resistor, our 1K resistor. This looks too easy, doesn't it? We can just write that the emitter current is then simply 4.3 volts divided by 1 kilo ohm, so 4.3 milliamps. We can write then that the base is equal to 1 over beta, base current is 1 over beta times the collector current, and the collector current is, how is that related to the emitter current? It is the emitter current times alpha, or alpha is beta over beta plus 1. So all of this to say that the base current is the emitter current over beta plus 1. And probably an easier way to see that, if that was confusing, is just to go back and draw the different currents here. You've got beta IB, you've got IB, and so what's coming out here is beta plus 1 of IB. That's the simplest way to see it. So what we have approximately, we'd have the 4.3 divided by 101, which is, I guess that's equal, and then we'll say that's approximately 43 microamps. Our last example in this lesson on large signal behavior of the bipolar transistor involves a combination of the previous examples, which leads to a new circuit scenario that we haven't considered before. So we have the emitter resistor like we have seen in the previous example, but now we've also added in a base emitter. And so this introduces a complexity that we haven't seen before. And the way that we're going to solve this now is we are actually going to write a KVL equation around this loop. Now we're going to assume the constant VBE model. And so we will write, going clockwise, we'll say minus 5 volts. We'll say plus RB times the base current IB. We're dropping 0.7 volts, so I'm going to write plus 0.7 volts. And then we will drop whatever the voltage is across the emitter resistor, and that will be RE times IE, and all of that is equal to 0. Now we have base current and we have emitter current in this equation, but those two are related to one another. So now we get to choose, do we want to solve for base current or for emitter current? I'm going to choose to solve for emitter current for now, so we need to express the base current and in terms of the emitter current. We just saw that right up here. So we saw that that's the emitter current over beta plus 1. So we're going to rewrite this. I'll bring the 5 volts over by itself. Actually 5 volts in the 0.7. So we'll have 5 volts minus 0.7. That's the net voltage that's driving current in a clockwise direction. And that is going to be equal to, we have RE plus RB over beta plus 1 times IE. And now we can write IE is going to be equal to 5 volts minus 0.7 volts, that's the VBE, divided by RE plus RB over beta plus 1. If we plug in some numbers for that, we'll see that we have, let's see, 4.3 volts over RE is 1K and RB is 50. So 50K over 101, and I'm going to approximate this because I'm lazy. So it's 1K plus approximately a half a K. So this is approximately 1.5 K, and that would lead to 2.87 milliamps in the emitter. And this would lead to then a base current of, what would that be, 28.7 microamps. Now we could have taken this equation and we could solve for IB. We would say that IE is equal to beta plus 1 times IB, and that would lead to 5 volts minus 0.7 volts equal to, and now we would have RB plus RE times, say I did that right, yeah, times beta plus 1, and all of that would be times IB. IB then is equal to the total voltage or net voltage in the loop divided by RB plus RE times beta plus 1. And we'd find this is going to be equal to 28.7 microamps. Now there's some important conclusions or observations we can make from this. And that is this idea of resistor reflection. Okay, so in the first case up here, we would say this is RB reflected to the emitter side or emitter terminal. And in this second case, where we're solving for base current, we have the emitter resistor reflected to the base terminal or base side. And so it becomes really easy to solve these biasing problems, even when you have resistance both in the base and the emitter. What actually is happening is that since the base current and the emitter current are tied or coupled one for one via the term beta plus 1, for that reason, the resistors, the voltage that is generated across the resistors that are in either one of these, in series with either one of these terminals, is also related by this beta plus 1 term. And so rather than always having to solve for either currents by way of doing this KVL, we can simply choose to take one of the resistors and quote-unquote reflect it over to the other terminal, and thereby be able to combine the resistors so that we get a simple expression that involves total or net voltage in the loop divided by net resistance in the branch. And the branch here will, sorry for the messy writing there, the branch will vary based on what current we're looking for. So if B, then it would be in the, all right, this way. If B, it would be in the base branch. And if we're going to do this for the emitter current, then it would be the emitter branch. So it becomes very easy to solve this. Let's just do one more, since I said this was going to be easy. So let's do a PNP example, and we'll end this lesson with that. Okay, here's an example using a PNP transistor. And first thing we notice is that we have a 10 ohm resistor in the emitter. We have a 1K resistor in the base. And the total voltage in our loop here is going to be 20 volts minus 0.7 volts. And the total resistance in the loop is going to be, well, it's either going to be 10 ohms plus the 1K reflected to the emitter side, or it's going to be the 1K with the 10 ohms reflected to the base side. So what we'll do, I'm interested in the emitter current. So we'll solve for the emitter current. We'll say the total voltage is 20 volts minus 0.7 volts. And the total resistance now reflected to the emitter branch is going to be the 10 ohms plus 1,000 ohms, but then reflected to the emitter side. So now you have to remember, do you multiply or do you divide by beta plus 1? Well, you can always remember that the emitter currents are much higher than the collector currents. Or I'm sorry, emitter currents are always much higher than the base currents. And hopefully that'll help you remember then that the resistances in the emitter must be much lower than they are in the base. So when we move from the base to the emitter, the resistance is going to be divided by beta plus 1. So this would be approximately 19.3 volts over 20, why not, let's just do it precisely. We'll say it is, we have 1,000 divided by 101 plus 10 inverse times 19.3, we get 0.97 amps. And so this is approximately 0.97 times 5, 4.85. Oh wait, I should say, take that back, let's write this out. 5 ohms times IE times alpha. Remember, I don't get all of the emitter current. So this is going to be 4.85 volts times alpha, which is going to be my 100 over 101. That's really not going to change it much. 4.8. There we go.